For this last section of projectile motion, we're going to look at objects launched at an angle. So in your notes, take a moment to draw the picture that I have here, and what we're looking at are velocity vectors. And what I want you to notice is that one, we have an object launched at an angle to the horizontal. So if we look at a horizontal axis, our angle would be down where I drew it. And then also on these vectors, you're looking to see that all of the horizontal parts of the velocity remain the same. And then vertically, we start out with quite a big velocity in the vertical direction. That component gets smaller and smaller until up at the top of the path, there's no velocity component in the vertical direction. And then as the object begins to fall back down, that velocity is getting larger and larger. You should notice some symmetry to a projectile that's launched at an angle. We are still in our perfect happy little physics world where there's no air resistance. So whatever happens on the left-hand side of our trajectory will be the same thing that happens on the right-hand side of our trajectory. The only thing that you're noticing is that the direction of the vertical velocity vectors change as they move downward. And so we're going to look at a couple of things that will be important about that. So if you consider an object launched at an angle, we do have this initial velocity at some angle to the horizontal, and then what I've done is I took the vectors from the previous slide, and notice the horizontal one is the pink one, and then the vertical one will be the blue. And what we're doing is breaking down that initial velocity into components. And we've actually already done this with vectors. We're just specifically doing that with velocity vectors this time. So the initial velocity that you're given would be the hypotenuse of a right triangle. The horizontal leg of the velocity can be found with the cosine of the angle, and we're using our subscripts to indicate which component of velocity. So to find the horizontal component, that would be Vx, and then that's equal to Vi, which is our hypotenuse, times the cosine of the angle. And then similarly, we would do the same thing with the vertical direction, but now we're going to use the sine function to help us find that leg of the triangle. So to find the vertical component of the velocity, we would label that as V with the subscript of a Y, so the Y lets us know it's vertical. And to calculate it, we would set that equal to Vi, which is our hypotenuse, times the sine of the angle that's given. As far as what you'll be asked to calculate on a test, you will need to know how to break down an initial velocity and an angle into the x and y components. So you need to know both of these equations for your next test. Everything on this slide can be termed as multiple choice questions that you might see in the future. So let's look at our picture. You should have that in front of you, the one that we drew at the beginning with all of the vectors. And there are a few things I want you to notice. The component that changes would be the vertical velocity component. Remember, it got smaller as an object traveled up, and then it got larger, that velocity increased on the way back down. And the reason for that was because of gravity. So gravity is making the object accelerate in the downward direction. So it slows it down on the way up, and then it speeds it up on the way down. The component that remained the same is the horizontal velocity vectors. So on those, because there is no acceleration in the horizontal direction, the velocity horizontally stays the same the whole time. That's going to be constant. Next, we have distances to compare. The range would be that horizontal distance or displacement, and that's something that constantly increases. So if I look at a projectile, the range would be the x direction, and it's the distance from beginning to end. So that would be considered the range. For the height, the object is going to go up to a maximum height, and then it's going to come back down. And we would label that with a Y. And now that we're dealing with two directions, you will see negative and positive signs pop up in some of the math questions, and up is going to be considered positive and down will be considered negative. For this last example problem, this will be a bonus question on your test, so if you're interested in doing the bonus question, keep watching the video, and I'm going to walk you through all of the steps on how you would work a problem for a projectile launched at an angle to the horizontal. If you are not interested in any kind of extra credit or doing a bonus on your test, then you can stop the notes now. Okay, for those of you still with me, let's get started. It's always helpful to draw a picture, so I'm going to go ahead and do that first just so we have something to kind of refer back to. That's going to be our horizontal ground. We've got an object that's launched with an initial speed of 4.5 meters per second, and it's launched at an angle of 66 degrees to the horizontal. And we can imagine that this projectile is going to continue through and then it's going to land on the ground somewhere about there. Now the first question you're asked to find is the flight time. So how long is the ball going to be in the air? Well, we only have two numbers. So before you actually start any of the parts to the problem, we want to go ahead and find the horizontal and vertical components to the velocity because that's going to give us a few more numbers to work with. So we're going to find Vx, and we do that by calculating Vi, which was given, times the cosine of the angle. And then we're also going to find Vy, which can be found with Vi times the sine of the angle. So I'm going to plug in those numbers and calculate that out. So if you followed along with your calculator, you should have gotten 1.83 for the horizontal component to the velocity and also 4.11 for the vertical component to the velocity. We also know another number, gravity. And remember that for a projectile launched at an angle, we've got an up and a down motion. So we need to distinguish up as being positive and downward motion is going to be negative. So which way is gravity? Good, it's down. So when we look at gravity being 9.8 meters per second squared for that acceleration value, we actually want to include the negative sign right here to let us know that gravity acts in the downward direction. So that's another number that we know so that we can go ahead and get started and find the time. Okay, we're going to do a little bit of a mathematical trick here to help us find the time in the air. We don't know a couple of values. We don't know how high it's going to travel, and we don't know what the range is, but if we think about our picture and the object moves from here to here, how much height does it have at this location and this location? This is when we would start timing and stop timing. Notice at both of those there is 0 height. So what we're going to do is let y equal 0 because there's no height when you start and stop timing. So let's plug that into our y equation. So back at the beginning of the notes from the last lecture, you should have y equals vyt plus half of gt squared. I'm going to go ahead and do a little bit of algebraic manipulation before I plug in any other numbers. So I'm going to subtract vyt to the side, and that's going to leave me with half of gt squared. And then notice that I've got a time on that side and t squared over here, so I can let that cancel out. And what that's going to do is leave me with negative 2 times vy over g, and that's equal to my time. So now that I've isolated the t variable, I can plug in my numbers. So I'm going to say negative 2, and then my vy was 4.11 meters per second, and gravity, remember, was negative 9.8 meters per second squared. And we need that negative sign so that those two can cancel out and we end up with a positive value for the time. And you should get an answer of 0.84 seconds, and this tells us how long the projectile is going to be in the air. Now let's move on to part B. Part B asks us to find the maximum height of the projectile. So remember our picture. Okay, that trajectory is going to look something like this, and we are looking for the maximum height right in the middle of the path. So we obviously know that we're going to need the y equation since we're looking for y, so I'm going to go ahead and write that down. And then there's a little trick that we're going to do. Notice that the y, the maximum height, occurs halfway through the flight. So when we go to plug in for the time, we're actually going to use half of that time value that we found in part A, because the time in part A was to travel from here all the way across, and the maximum height occurs halfway in between. So I'm going to write that down as a note for you. So again, when we plug in our values, we're going to use half of the time because the maximum height occurs halfway through the flight. So I'm going to go ahead and plug in my numbers and solve the equation. So I wrote in some of the tricks in different colors to point them out. For the t values, you're using half the time, and then don't forget that gravity is negative. And you should have ended up with a maximum height of 0.86 meters. Now for the last part. Part C is asking us to find the range, which would be the horizontal distance traveled. So remember our picture, it looks something like this, and we are looking for the distance from where it started to where it fell back down on the ground. The x equation is really simple. We're going to say x is equal to vxt. We found the horizontal component to the velocity at the very beginning, and then for our time, we are going to use the full value of the time because that range is for the entire time that the object was in the air. So I'll plug in those numbers and see what you get. After you've plugged everything in, you should get a range of about 1.5 meters. So again, all 3 parts to a question like this will be a bonus question on your test. So if you have any trouble with that and you'd like to go over another example, just come in and let me know and I'll be happy to go over that with you. Good luck.